Welcome to the Calculus AB video for skill number 153. I can use calculus to determine increasing and decreasing intervals. And the trivia question for this video is, we've learned that this part of the temple is called the architrave. Trivia question is, what are these little droplets called? Alright, so this video is talking about where a function is increasing and decreasing. And very generally, if I have, we'll say, some curve like this, that is, we've got an area where it is increasing, and then an area where it's decreasing and increasing. The ultimate goal is to be able to tell what the intervals of increasing and decreasing are. So the general approach is we want to find where we have critical points, because those are going to be locations of a horizontal tangent line. And we'll say this first one occurs at 2, and maybe the second one occurs over here at 5. And in this case we would have a function that is increasing from negative infinity to 2. It's increasing, and then we've got it decreasing from 2 to 5, and then we have it increasing from 5 to infinity. And the general concept behind this is the slope of tangent lines is positive here. So f prime is greater than 0 when it's increasing. F prime is less than 0 where it's decreasing. And again, we've got a portion where we're increasing, so f prime is greater than 0. So the overarching idea to find intervals of increasing and decreasing is we would want to identify our critical points, points where the function derivative actually equals 0. And then we would test intervals between those critical points. So we also have the potential for critical points where there's a break in continuity. So we'd want to also test those values. And in this case, if I included this black portion of the graph, then of course my interval here would need to change. Alright, let's take a look at this on the worksheet. The instructions say find the x-coordinates of all critical points, find all the discontinuities, and then find the intervals where the function is increasing and decreasing. So this is going to kind of walk us right through the process. Let's start with problem number 2. So fortunately, problem number 2 is a polynomial, so we know right off the bat that it's continuous everywhere. So let's find our critical points. And you might recall the critical points occur where the derivative is equal to 0. So I guess in this case it's not a function f, it's a function h. So we want to find h prime first, and in this case we take the derivative and we get negative 3s squared plus 4s. And we want to ask ourselves, when does this derivative equal 0? It's a lot like when we were finding our max and min, our relative max and min. So we set this equal to 0, and we could factor an s out and get negative 3s plus 4, which means this whole function is equal to 0 at s equals 0 and at s equals 4/3. So those are our critical values. We have no discontinuities, so the only intervals that we need to test are around the 0 and the 4/3. So the way I do this is I make a number line with 0 and then 4/3, and I test values for this. So I'm going to test what is the derivative of something less than 0, what is the derivative of something between 0 and 4/3, and what is the derivative of a number after 4/3. So we'll go with 2. And again, I really should be saying h prime since our function is h. H prime, h prime, h prime. So if we stick -1 into the function, we're going to get a -1 times a +7, so that is a negative answer. If we stick 1 into the function, we're going to get 1 times +1, so that's a positive answer. And then if we stick 2 into the function, we're going to get 2 times, what is this, -2? So 2 times -2 is a negative answer. So there we have our increasing and decreasing. So a negative slope means that we are decreasing. A positive slope means we are increasing. So the conclusion that we draw in this problem is we are increasing on the interval 0 to 4/3, and we are decreasing on -infinity to 0 in union with 4/3 to +infinity. So there's our intervals of increasing and decreasing. And this pretty much is how all of the worksheet works. I'll do a couple more for you, but let's take a look at number 4. Alright, so number 4 is the cosecant of s. So if we wanted to identify our discontinuities, it would probably be useful to think of what the cosecant graph looks like. And if you remember, cosecant is 1 over sine. So if our sine graph looks something like that, then our cosecant is going to be something kind of like that. So it's useful or helpful to remember what the graphs of these functions look like. We are interested in the interval from -pi to +pi. So from -pi to +pi. So that's the interval that we're interested in. So we're capturing these two pieces. Looks like we'll have 2 spots where we're increasing and 2 spots where we're decreasing. But let's go ahead and find our critical values. So our critical values occur at where g prime is equal to 0. So the derivative of cosecant. That's a good challenging one to try to remember. Negative cosecant s times cotangent s. And we want to find out when is this equal to 0. When is cosecant s times cotangent s equal to 0. And that's maybe somewhat tricky to evaluate off of understanding trig functions, but we could write it in terms of sine and cosine, and then it becomes a little bit easier. So cosecant is 1 over sine s, and cotangent is not sine, cosine over sine. So cosine s over sine s. And if we wanted to know when is this function equal to 0, that would occur whenever the numerator is 0. So we'll ask ourselves, when is cosine of s equal to 0? And various people have different methods. I go to visualizing what the graph looks like, and I see that it equals 0 at pi over 2 and negative pi over 2. So our critical values are at pi over 2 and at negative pi over 2. The points where we are discontinuous is at negative pi, 0, and pi. So you could argue that all of our critical values are negative pi, pi over 2, 0, pi over 2, there should be a negative there, and pi. Because we have our 2 critical points and then our 3 discontinuous points. And if you list them out like that, you're helping set up your increasing, decreasing table. So then we want to test our intervals, and a number between negative pi and negative pi over 2 might be, we'll go with g prime of negative 3. This one we could do g prime of negative 1, g prime of 1, and g prime of 3. And we don't need to test the other side because it's outside of the scope of the interval they're interested in. If you evaluate g prime of negative 3, you're going to find that that is a positive value, and then we have a negative value, and a positive value. So the conclusion we draw is we have increasing intervals from negative pi to negative pi over 2, as well as pi over 2 to pi. And we have decreasing intervals from negative pi over 2 to 0 and 0 to pi over 2. And it's important that we break it here at 0 because we have a discontinuity there. So something else that we can draw when we're doing this, or something else that we can figure out, is relative maxima and minima. And what we have here is a case where we're going from decreasing to increasing, which means the curve is going down, and then at this point it starts going back up. So decreasing to increasing tells us the location of a relative minima, whereas in this case we have increasing to decreasing, so that would be a relative maxima. So we've located max and mins, and this concept of a local or a relative max or min occurs when the first derivative changes signs is called the first derivative test. So we use the first derivative test to locate the locations of our relative maxima and minima. Okay, let's move on to problem number 6. Problem number 6 is nice. It's another polynomial, so we know polynomials are continuous everywhere, so we can just move right into the problem of finding our critical points. H prime of s is negative 3s squared plus 8s, and we want to set that equal to 0. So if I factor out the s, negative 3s plus 8 equals 0, so I'm going to get critical points at s equals 0 and s equals 8/3. So I can set up my intervals from 0 and 8/3, and I do test points h prime of -1, h prime of 1, and h prime of, we'll just go with 5, we'll say. You can test any point you want to as long as it's within that interval. So in this case, if I stick -1 into the function, I'm going to get a negative answer. If I stick 1 into the function, I will get a positive answer. And if I stick 5 into the function, I get a negative answer again. That tells me we have, by the first derivative test, we have a local minimum at 0, a local max at 8/3, and it also tells me that I am decreasing from -infinity to 0, as well as 8/3 to infinity, and I am increasing from 0 to 8/3. So my function decreases all the way to 0, then it starts climbing up to 8/3, or over to 8/3, and then it starts dropping back down. So maybe it looks something like this. We'll get in later on in the chapter or unit into drawing a graph using calculus to draw the graph, but for now you get the idea where the function is decreasing, and then from 0 to 8/3 it's increasing. How far up or down the y-axis this graph is another side project. Okay, let's move on to problem number 8. Alright, problem 8, something that's not trig and not a polynomial, so we might have a discontinuity, and if we look closely we see there's a denominator, and that denominator usually indicates that there's some sort of place of discontinuity, and in this case a 3 would be my discontinuity. But otherwise everything else we do the same. We're going to find f prime. We can do the quotient rule, and I encourage you to do this on your own. You'll find that it becomes -2 over s minus 3 squared. And if we want to set this function equal to 0 to find the critical points, we would go about this and say, when is this equal to 0? Well, that would occur when the numerator equals 0, and the numerator never equals 0. So that means there are no critical points. There's no critical points, but we do have a discontinuity at s equals 3. So that's the only point on our line that we need to test. So we're going to stick 3 there. We're going to test, we'll do f prime of, we'll say 0. Zeros are often easy to deal with. And f prime of 10. And if we stick 0 into the function, we would get -2 over the value of -3 squared. So that is -2 over +9. And if we stick 10 into the function, the derivative function, we get a negative over a positive, so that is also negative, which tells me that the function is decreasing from -infinity to 3 and from 3 to infinity. And again, we need to remember to split that because we have a discontinuity here at 3. So for those who are familiar with the graph of this function, this is a reciprocal function that has been shifted to the right 3 units. So we actually have something which kind of looks like that. And you can see that this function is decreasing everywhere. So it's sometimes useful to see if you can visualize what the graph looks like to confirm your answers. Finally, let's look at problem number 10.
Calm down. What does that even mean? Can you relax?
I'm a scat man.
Looking at problem 10 and 12, those both look like polynomials. Nothing too out of the ordinary. Number 14 looks like a trig function. Also not any different than ones I've done before. So I'm going to leave it to you to do the remainder of the problems. Maybe if you get stumped on one, we can do it in class. Just go ahead and ask in class. Alright, thanks for watching the video. Hopefully in watching it you've kind of picked up and retained what the first derivative test says. The first derivative test. And we will soon learn about a second derivative test. But the first derivative test, and we should be able to take a look at a function and determine when that function is increasing or decreasing. The answer to the trivia question is these little droplets found in the architrave are called gutta. G-U-T-T, and then A, the plural would be with an E at the end of it, gutta. Thanks for watching.